You're listening to WMPG 90.9 Forum Portland, 7 Maine Community Radio from USM. Live from the Orion Cygnus arm of the Milky Way galaxy, this is Scientifically Speaking, a weekly half-hour program devoted to elegant curiosities, and I am one of your hosts, Sarah Chang, and joining me as always is Bernie Rhyme, DJ Starwatcher. How are you, Bernie?
Yes, hi Sarah, very good, thank you.
Bernie is our professor of the Astronomy Lab at USM and our local protector of the night skies. Reach out to us at WMPG Scientifically Speaking at gmail.com or on Twitter at WMPG Sci Speak. And you can head over to WMPG.org to find the last 5 weeks of archives of all of your favorite shows, including this one. Bernie, could you let our listeners know what is up in the night sky for the next week?
Yes, okay, certainly. So today will be Friday, November 26th, the Friday after Thanksgiving, also known as Black Friday. So we have just about a last quarter moon. It's technically actually waning gibbous. Remember, of course, we had the full moon on the 19th that had the lunar eclipse. Unfortunately, it was cloudy and rainy. I think it cleared up right at the end at 4:30, so I tried to get up and it was rainy, so I didn't stay up. Some of my friends saw it out in Vermont, and maybe some people might have seen it in this area, but I don't blame them if they didn't. So we're a week past that, so just about last quarter moon means it rises just before midnight and sets about noontime. And we still have the three planets. Venus sets right after sunset. And then we have Saturn and Jupiter in that sequence. And of course, notice that Venus is getting closer and closer. Actually, by next month, it'll be about 18 degrees away, and Saturn will be right in the middle. So those three will form a perfect line, just about evenly spaced, but that's still a few weeks off. But you can watch that whole process unfolding. And then, let me see, the days are getting pretty short, so the sun rises like 7:15 and sets at 4:08, which is just about the earlier sunset already. So the days are just over 9 hours long. They'll get just under 9 hours long. We're only like 3 weeks to the winter solstice. And then just as a brief thing to start looking for, you won't see it without binoculars till probably next month, but if you have some other method, there's a comet called Comet Leonard. It's supposed to get really bright, and I'm sure a lot of people in our club, and hopefully several of our listeners will try to watch this. It may get as bright as 4th magnitude, which is like 6 times brighter than naked eye visibility. Even if it gets to 5th, it'll be easily visible. If it's 6th, it'll be on the limit. It was found only a year ago when it was 19th magnitude, or a million times fainter than what we could see. So it's be getting brighter, and we predict it'll get brighter. It'll be pretty close to Earth and really close to Venus, and it'll actually be physically close to Venus in the sky at some point next month. So just something to look forward to. Maybe a few leftover Leonid meteors. I didn't see any because the moon was full, obviously, the last few days during the eclipse. So that's about it for this week.
Awesome.
Yep.
And Bernie, I feel like it's always helpful to remind, because I get this question all the time, but what exactly is a lunar eclipse? Like, what's going on?
Oh yeah, okay, good, thanks. Actually, we just did a lab in my class on eclipses, so it was perfect timing. Of course, I talked about the solar eclipse that we both got to see, but I got into a little bit more detail. And the lunar eclipse was happening at the end of that week that we did the lab. Okay, so technically you're seeing our shadow projected onto the moon, which is pretty neat if you don't think about it. Now we have a darker part of our shadow called the umbra, which is when you see the partial phases. We have a lighter part called the penumbra, and even though the moon started going through that around midnight, you really couldn't notice anything until it got into the umbra. And then when you get the nice color, that in a dramatic way, what you're really seeing, because the atmosphere is bending the sunlight back onto the moon, you're seeing the combined effect of all the sunrises and sunsets on the Earth at one time projected onto the moon. So that's a really dramatic way to look at a lunar eclipse. It tells you about the nature of the atmosphere at the time. It's a nice sight to look at. It's scientific, it's artistic, it's everything else. And the next one is, I think, next November. We've got about a year to go for the next one.
Gotcha. Well, and then I guess in another 2 years, we'll see solar eclipse right here in our neighborhood.
2.5 years, yeah, April 2020.
2.5. Oh, two. Dang. Okay.
2.5.
A little longer.
Yeah, I have it up on the board for my students. It was like less than 3, and now it's less than 2.5. And
yeah. I think I did try to go in my, for work, tried to block that time off, but
oh yeah, well definitely.
I think it was too far ahead. I couldn't do that.
Oh yeah, well but it should be a national holiday. I mean, so everyone, and even school. I'm one of the people at our club. He's a teacher at St. Anselm's. He was taking a physics final the day of the and he was so upset his professor wouldn't even let him go out for 2 minutes. We had to take the final.
Oh,
That
no.
was the annular, and he needed a filter, but it would have been nice to even see an annular eclipse. He wouldn't let him go out. So if
Well,
there's no
Bernie,
school,
yeah, we should petition for that
yeah,
and make it a state
yeah,
holiday.
yeah. At least they, preferably national, but at least a state one would.
Yes,
If
at
we,
least state. I
yeah,
think Bernie, we should just start there.
yeah, okay, we'll start with the state of Maine. They're pretty keen.
Well,
But,
thank you so much, Bernie, for
yeah,
that What's Up in the Night Sky.
welcome.
If you could not take notes fast enough, you can also check out the monthly What's Up column in the Portland Press Herald. So, happy Thanksgiving, everybody. Today, we celebrate here at Scientifically Speaking on WMPG 90.9, we celebrate Black Hole Friday. This is our day to talk about black holes, these wonderful, very scary monsters in our universe. And I did want to start off with this quote by Carl Sagan. If you wish to make black hole jets, you must first create magnetic fields. Black holes were one of the first and most extreme predictions of Einstein's general theory of relativity, founded in, or I guess he first kind of announced that in 1915.
Mhm.
And, here today, we just want to celebrate black holes and talk about some of the work that's been done in the past year. We try to do Black Hole Friday every year and call out some of the folks who've been involved in advancing science and understanding of black holes and new things. For example, we'll talk about how we might be able to determine the masses of black holes today and some of the new techniques that are out there. So, Bernie,
Mhm.
as our local astronomy teacher, could you help
Mhm.
our listeners understand what exactly a black hole is?
Okay. Well, so they should probably first be aware that there's several different kinds, so they don't mix up the supermassive ones at the center of galaxies with stellar ones and even smaller ones. It's like a whole range. So first, there's actually like four different types. So the first one is theoretical. I think it's there. They haven't found it. It's hard to find. It's called a primordial black hole. So
Mm.
these, if they're there, started when the whole universe first came at the Big Bang. They would be older than atoms. They would, if at the size of a proton, it would have the mass of an entire mountain, like trillions of tons. So it would be really dense. And actually, it could be what dark matter is. If we actually ever find one of these primordial black holes, really tiny and super dense, they could be what dark matter is. So that makes it kind of interesting. I don't know if there's any experiments set up with that potential, but that's one kind. So that's the kind, they would be everywhere and wouldn't really have to worry them. Obviously, we're not going to fall into them. They're smaller than a proton, but they could be there. All right, and then you have the one that probably most of us think about. That's called a stellar mass black hole. So a really heavy star, about 3 times the mass of the sun, are the lightest ones, and then it goes up from there. When they end their life, they don't only turn into a neutron star and a supernova, they would actually drop out of the fabric of space-time, and they would turn into a black hole, which is, if it's the size of the sun, it would probably be about 10 miles across. Okay, so that would be the physical size of it. And
Wow.
now, if you turn the Earth into a black hole, it would be about the size of a marble, like 2 inches across. So that's the density. And the neat thing about black holes, theoretically, according to Einstein, any piece of matter you could turn into a black hole. Like if it's your coffee cup, obviously it would be really tiny, you wouldn't see it. If you take the entire Earth, it's a marble. If you took the sun, it's like 10 miles across. So that's the stellar mass black holes. There's quite a few of them. Maybe 1% of 1% of all the stars in our galaxy would go that way because they were that massive, and that's what happens to them. Then you have the supermassive black holes, which are at the center of just about every galaxy, except for maybe the really tiny ones. Every galaxy has a supermassive one. Our own Milky Way has one that is called Sagittarius A star because it's in Sagittarius. It's 4 million solar masses, and basically it has a radius of about the size of maybe roughly the sun to Mercury. So that's the radius of the black hole. Because they get bigger as they have more mass, and we can figure out the mass based on how the stars orbit around it. And of course, we're not seeing the black hole because nothing can escape, but we're seeing the shadow that the radiation of it is casting from the black hole. We're seeing that on the rest of the galaxy at the center. So that's pretty
Mm.
neat. And then, actually, I just found this out. We have a whole nother class which gets way bigger. Those are called ultramassive black holes, and they're also at the center of the galaxies, but instead of a few million, they can be as many as 100 billion solar masses. So
Wow.
they're literally so much bigger. And the biggest object now, we think, in the entire universe is one in the galaxy in near the Big Dipper. It's called TON 618, and the ton, I'm sure it doesn't stand for ton, but it's almost 100 billion solar masses. And so that black hole would be 11 times the size of our solar system. So almost
Wow.
like a light year across. It's the biggest object, and it's that dense and that solid and that huge. And of course, it would almost never, it would eventually evaporate, but like in, Google's number of years before something that huge would ever disappear. And there could be far bigger ones than that. So that's a whole class beyond just the ones, the supermassive
Yeah.
ones.
How does TON 608
Mhm.
influence us or impact us? Do you know?
It probably doesn't, because even the one at the center of our own galaxy doesn't. That's 30,000 light years away. The one
Mm.
we took a picture of is 55 million. And this one is like, this one is 18 billion light years away.
Mm.
It's further, because as the universe expands, it can be further than the age. So
Yep.
it's way out. It's basically a quasar because they're really powerful in a really small amount of space. It's basically a quasar. The universe is 50 billion light years in radius, and this is a good fraction, and the redshift number would be up there. So that's
Mhm.
so far away, it really wouldn't influence in
Yeah.
any detectable way. Of course, in some way, it influences us, like even gravitational waves would do.
Yeah.
So that's a whole new class of really super massive black holes.
So the ultras, what was it? Ultra
Ultramassive.
supermassive? Ultra massive.
Ultramassive. I mean, I thought it kind of ended as supermassive, but then there's one that's like even another 10 times bigger than the one at M87. That's
Yeah.
ultramassive. And I
Yeah.
never heard of Ton 618 before this either. that's, and the 18 billion light years away. I mean, but we can see it because it's that powerful and,
Yeah.
gives that much energy and light.
Very cool.
Yeah.
Speaking of, you had mentioned one of the supermassive black holes was Sagittarius
Mhm.
A star, which is at the center of our galaxy. And I think we just want to put in a plug for this because the James Webb Telescope is coming out. It's launching what, December
December
18th?
18th,
December 18th.
couple, 3 weeks
And
away.
yeah, yeah. And so we have been using a network of telescopes essentially to look at black holes. And with the launch of the James Webb telescope, the James Webb telescope has the capability of capturing data in two infrared wavelengths simultaneously and continuously from where it will be, which is a little bit beyond the moon. And the web will also have basically uninterrupted view of everything. And so we can observe cycles of flaring and calm, etc. And that will be kind of one of the biggest advantages of observing Sagittarius A star once the web gets out there. But it'll take some time to get there.
Yeah, the Hubble went through cycles of dark when the Earth got in the way because it
Mhm.
was in low Earth orbit. It was only
Mhm.
like 300 miles up. The Webb will be over 1 million miles away. So nothing's
Yeah.
going to get in this way, like you said.
Yeah. So I think during some of the first observations that the Webb telescope, the astronomers will be using that infrared imaging power to essentially address some of those unique and persistent challenges with the Milky Way, with our black hole, our local black hole, our little little pet black hole, Sagittarius A
Yeah, a
star.
little. I know, only 4 million versus 100 billion. Huge difference. It may
Exactly.
also tell what they really are, which is neat because, I
Yeah.
mean, they could be just condensed space time, it could be plasma, they could be all kinds of
Mhm.
different things. And they
Mhm.
may actually be able to prove that. It'll take about a half year to get actual data. And we'll
Mhm.
give you a lot more updates about as it's going up there and after it launches and all the things it has to go through. So
Yeah.
don't expect data like the day after or anything. So, yeah.
So speaking of another famous black hole, earlier this year, and I will share this with our listeners at some point. M87 is a big, very well known black hole. It's Messier 87, and it's in the constellation Virgo. It's about 55 million light years away from us, and I believe it is only what 6.5 billion times the mass of the
Yeah.
sun.
Only.
Okay. Yeah,
Bigger
well, at
than
first I
anything
thought it
other
was
than the
6.
ultra ones. It's huge.
So would this fall under the category of supermassive or
I think
ultramassive?
it's the top limit of supermassive. It's
Okay.
about the size of the solar system. The ultramassive are 11 times the solar system, like almost twice.
Okay.
Yeah, 11 of
Okay.
our entire solar systems can fit into that. In the one at M87, about one solar system.
Wow.
It's still pretty big.
Just
At that,
one.
that yeah, at
That's
that density,
pathetic.
to still have that kind of size, it's just amazing.
Right, right. So M87 is also called Virgo A, and it is the first black hole that was ever directly imaged. And it is also kind of the source of tons of radio energy that comes from this Virgo cluster, and also a powerful X-ray source. And again, like all black holes, the gravitational field is so strong that not even light can escape. And so, earlier this year in March, one of the astronomy photos of the day that I know, Bernie, you love sharing with your
Yeah, I
class.
do the class every night. Yep.
And March 31st, the featured image was this M87 taken in polarized light. And so basically what they did was the polarization is kind of produced by this powerful magnetic field surrounding this supermassive black hole. And the radio waves were detected by the Event Horizon Telescope, which is essentially that network of telescopes, radio telescopes distributed around the world. And so it mapped out using kind of computer generated flow lines the structure or the radio waves that come out of it. And basically they mapped that on top of the original famous black hole image in 2019. And it's just very cool to see how the field kind of circles around the black hole. And it's just very, very, very beautiful. So I'm going to share that with our listeners, and definitely check out that astronomy photo of the day. And then, as a reminder to our listeners, Bernie, last year there were 3 Nobel Prizes given to some physicists, some astronomers,
Yep.
Astrophysicists, I guess, for their work with black holes. Do you want to give our listeners a little overview?
Yeah. So Roger Penrose got one. He teaches at Oxford while he's like in his 90s, I think already, or late 80s. So
Mm.
he was the first one to actually prove mathematically that the black hole exists based on how the lines converge at this point. I mean, I don't know the math behind it. It's pretty extreme, but he proved that. And then the other two were Andrea Getz. I think she teaches at UCLA, and then
Mhm.
Reinhard Genzel from Germany. So basically, their work, it wasn't recent. They had done a lot of work on Sagittarius A star, getting the mass of it and seeing how all the stars go around almost in real time. I mean, normally, of course, it would take several years, and to go around. It's a quarter of a million years for us to go around the center of our galaxy. These stars would go around like in a day or two. So that
Yeah.
was pretty obvious. Yeah. So so based on that, that they got the Nobel Prize on black holes. This year, of course, it was on the thing with climate modeling and that type of thing.
Right.
We went
Right.
about that a little
Yeah.
bit, but yeah.
Yeah, so definitely check that out. And then we love Dr. Gez. She also, in case you didn't know, she's one of the authors of a children's book called "You Can Be a Woman Astronomer." So great gift if you're looking for one for the holiday season. Just a plug out there.
Okay, right. Plug your book there.
So yeah, Dr. Penrose, Dr. Gez, and Dr. Genzel are our 3 winners from last year for their work on black holes.
Mhm.
And then the other thing that I wanted to share with listeners was the weighing of a black hole. So how do you put a black hole on a scale and figure out how much it weighs? Because Bernie, you're talking like, oh, this is 58 million mass solar masses.
Yeah.
Well, like how do you actually get to that number? And I know you were kind of talking about how currently
Yeah.
determine the mass of a black hole, which you were talking about how the stars.
Yeah. How fast they orbit near it.
Mhm, mhm.
Yeah. Yeah.
And so M87, let's go back to M87
Mhm.
again. So it's about 55 million light years away. And it was also the first black hole whose mass has been calculated by 3 different methods. One is by, like Bernie said, measuring the motion of the stars. One is by the swirl of surrounding gases. And now there is and then a third method was that you can measure the diameter of the black hole's shadow. And so that was one method that came out of the Event Horizon Telescope Imaging Project as well. And there's a little bit of a history here, which I find a little bit interesting. So the first mass estimates to track the motions of stars whipping around the gravitational center was in 1978. And for M87, I believe the original mass was about 5 billion times the mass of the sun. So that was the first estimate. And then in 2011, using similar stellar techniques, but a little bit more precision, bumped that size up to 6.6 billion times the mass of the sun. And then going back to 1994, there was a different method that tried to trace how gas is close to the black hole, closer to the black hole than the stars that swirl around it. And this technique then suggested that the black hole was about 2.4 billion solar masses. And then in 2013, that was then revised to 3.5 billion. So a lot of estimates here. And so for many, many years, people were like, oh, which way is what's the best technique? And so I believe, I don't remember when this was, but a couple years back, the Event Horizon Telescope then was able to look at the shadow of the black hole that it cast. And so basically using that, it yielded a diameter of about 38 billion kilometers for M87. And astronomers then were left to, they were able to calculate a mass of 6.5 billion suns, which is very close to the mass suggested by the motion of the stars. So several ways to measure the mass there. Any of that sounds familiar to you, right, Bernie?
Yeah, I knew of the first method, but not some of the other methods you just
Some of the other
mentioned.
methods, yeah.
Yeah.
Well, clearly we can see that some of those other methods weren't very precise.
Yeah. Yeah.
But there's been a new technique. So there's a new way to weigh black holes. And this method could be applied to any astrophysical object with an accretion disk. And Bernie, can you let our listeners know what the accretion disk is for
Yeah.
some of our
Well, like
objects?
another object that would have that would be when you have a white dwarf pulling in energy from a red dwarf, that would go with called a Type 1a supernova when it explodes. So those are used as cosmic distance indicators because they always explode at exactly 1.4 solar masses. An astronomer from India figured that out, so you can really use that. So, I mean, obviously it would form a disk because the matter can't get in really that fast, so it has to spin around and heat up. So that's the accretion disk, and the size and the speed of all that would be depending on the source of the black hole, or in the other case, the source of the white dwarf and the red giant that are forming that pair as the accretion disk forms. So,
Wait, yeah. So what happens is that Dr. Colin Burke, he's an astronomer at the University of Illinois, Urbana-Champaign. He found, or he's kind of describing that the actively feeding black hole, so a black hole that's eating everything up around it, surrounds itself with this disk of hot gas and dust, and that actually flickers like campfire. And astronomers have actually found that monitoring changes in those flickers can reveal something that is really hard to measure, which is the heft of these black holes. And so there the time scale of this flickering is, depending on the size, can be anywhere from hours to years. Obviously, with really large, your ultra massive ones, it might be years to kind of observe that flickering. But it could be related to the size of the black holes. And so that's essentially what Dr. Burke did for some of his work is they basically assembled observations about 67 actively feeding black holes with known masses. And these range from sizes of 10,000 to 10 billion solar masses. And for the smallest of these black holes, the flickers changed on timescales of hours to weeks. And supermassive black holes with masses between 100 million and 10 billion solar masses flickered every few hundred days. And so that gave them the hint that, okay, if this relation holds for small supermassive black holes and big ones, maybe it might be a universal feature. And so, like Bernie, you were talking about the white dwarfs. This
Mhm.
team also looked at white dwarfs, and they're because they're some of the smallest objects that also have accretion disks. They actually followed the same relationship between flicker speed and mass. And so, what they analyzed didn't cover the entire possible range of black holes. Obviously, it was only about 100 to 100,000 times the mass of the sun. What they've seen is that there does seem to be this kind of relationship, and it potentially, this relationship between the flickering and the mass could tell astronomers what kind of disk flickers to then look for to help bring kind of some of these hidden black holes out of hiding.
Mhm.
And yeah, so it offers kind of this simple way to weigh the black holes than any other previous technique, but not necessarily a faster one, because like they mentioned, very large ones would probably need hundreds of years of data collection to make that determination, and you could probably do some calculations before you die. I mean, if that's kind of,
Just
to
use it
then
that
reveal
easy.
the masses. Exactly.
Yeah.
There.
What's actually even more interesting than a black hole is if you have two of them that are connected or entangled, then you get the wormhole. Because
Mm.
based on Einstein, he didn't only predict the black holes, which we found later. Actually, someone named Schwarzschild actually found them just about 1916. So he was the first one to really apply his mathematics to prove the Schwarzschild radius is the event horizon. So he did as a contemporary of Einstein. But since then, we found a lot of neat new things out, like you said. So the wormholes, I think, are far more interesting because if space-time is like flexible, which it is, it's not like a stage everything happens on. The stage itself is an actor in the universe. So since it's flexible, you could bend it like a piece of paper and just connect two parts of it. So you could go to the edge, that TON black hole that we talked about. You could go there. Like it's 18 billion light years away, but you can go there in a split second if you
Mm.
can connect that. So wormholes, I mean, they haven't actually been found per se, but they're certainly theoretically possible. The key there would be to keep them open because gravity wants to close them, and to keep them wide enough to put anything of a size of a spaceship or a person through it. Right now, you can't even put a proton or an atom through it, and they do tend to close up, pinch off again. So you want to keep them open somehow. There's different ways theoretically they can do it before we actually find one that can prove this. So there's something called exotic matter, which basically is like dark energy, which has a negative mass. So that would be repulsive. It's anti-gravity, which is what the whole universe is doing. So the stuff is here. It's everywhere, actually. On a bigger scale, you notice it. You don't notice it here. But if you can make that happen on the scale of a wormhole, you could keep that open enough, then you can get to any part of the universe in like no time flat. It's the entangled. You take like the smaller version would be entangling an electron, and the biggest version of it would be entangling black holes. As long as they're spinning, then you can create that wormhole. So that's a really unique. Those are like you can figure out which two electrons are entangled once you create them and polarize them. So if you
Yeah.
can figure out which two black holes are entangled and keep that wormhole open, which is the next big challenge you have to do, and then you can go anywhere in the universe in no time. Not even doing the Einstein twin paradox. The faster you move, the slower time moves. So if something's 4 light years away, yeah, you can get there in 4 years.
Yeah.
But this way you can get there in literally no time. So
That's
that's the really
awesome.
fascinating part of it. Yeah.
Very cool.
Yeah.
Neat.
Yep. So
Well,
they're all realistically theoretic. I don't think we aren't advanced enough to do this.
yeah.
But just the fact that we're learning about it, that the entangle comes in, that the dark energy could be the key of what we need to keep them open at any scale. I mean, probably we want to do it in a lab first before we actually go anywhere out in space per se. We can do all this in a lab first, like they did with
Yeah.
lasers, and they can slow light down to walking speed. They have the Bose-Einstein condensates that are almost a trillionth of a degree above absolute zero. We can do all this stuff in the lab, and all has some practical applications. But you do it in the lab first.
Yeah.
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 Very cool.
Yeah.
Well,
Hmm.
listener, we hope that you learned something about black holes today on this very fine, hopefully it's a fine Black Hole Friday. And with that, you have been listening to Scientifically Speaking here on WMPG with myself and Bernie. Stay tuned for Something for the Weekend with Anila. And from your favorite nerds, just a reminder to vaccinate, to mitigate, and then we can all congregate.